My pleasure to introduce Berry Wen. Berry's a new faculty member here at Stony Brook. Arrived this summer, but officially here with her position here starting.
Hello. Every time I don't know how to. Hello, can you hear me?
Yes.
Okay, great. Yeah, so I follow the instruction. Yeah, when Brian wrote me the email asking me to present one project. So I chose this one. Yeah, I chose this one because it's funded by NSF and I've already developed some progress. So the method is actually also adopted by one NASA project and the recently funded DOE Genesis mission. Yeah, so the whole idea is very simple. Downscaling. Yeah, and for this one, it's precipitation. I use precipitation as the example because precipitation, everyone knows is chaotic system, very difficult. Yeah, the most challenging one. Okay, yeah, motivation is very simple. Everyone loves high resolution, right? Yeah, so not only this one, but in our research. And also from my own research, we found high-resolution geoscience data are essential for understanding atmospheric dynamics and improving their predictions, particularly for high-impact extreme weather. Yeah, everyone here understands, yeah, if we look at some extreme weather, but if you smooth it out to a larger area, then the peak value will be lowered, right? Yeah, so this is a problem. Yeah, we don't know where the intense core is. Okay, and also my research shows that, for example, for precipitation, if we look at the lower spatial resolution, it could cause as high as like 20% bias. And if we apply this precipitation to hydrological modeling, and so the flash flooding, we may for the underestimation of peak discharge, it can be as much as 43%. Yeah, so this kind of bias or errors caused by resolution could be very high. Yeah, so this is the whole motivation, and we are thinking about to do the downscaling, yeah, to get the high resolution precipitation data. And when we are doing the model, we have our wish list, right? The first is accuracy, right? Yeah, so we want something when you have the downscaling, it's accurate, reliable, so we can use it. Okay, and also we want it to be efficient. Yeah, for a lot of models, of course, you can use a physically based downscaling model, but it always takes a long time. But we want it to be fast. Okay, yeah, and the third thing is generalization. Yeah, so this is something very important in my understanding. For example, you have some fine resolution data in Oklahoma, right? You already have that, and then you use this ground truth to train your data, and you are successful. And then when you are going to a data desert region, if you do not have the high resolution data, then you said, okay, then what can we use to train, right? So you want to have some model reliable. When you train it in Oklahoma, you can transfer it to some places you do not have the high resolution data. Yeah, so this is a generalization. So I have this kind of three things on my wish list, and we can go over it one by one. Yeah, and so this is actually the first try. We use the model, diffusion model, the AI model to do the downscaling for temperature. Yeah, and this one is all model data from 9 kilometers to 3 kilometers in California, and this one is ground truth. And this one is our AI generated fine resolution temperature. Yeah, so this one is the first result we got from our students. And when I saw it, I got like, oh my gosh, what a magic. Because from this kind of 9 kilometer to 3 kilometers data, only diffusion model, one AI model applied without other inputs. Yeah, so it works, and I got excited. However, this is temperature, right? Everyone knows temperature, right? The variation is not that dramatic. My background is precipitation. So I want to say, can we apply this model to precipitation? Yeah. before we jump to precipitation, maybe I should give you a little bit of background about diffusion model, this magic box. Okay, I'm trying here. You know what? If you want to know more details, go to ChatGPT. Okay, yeah, ChatGPT give very accurate and detailed explanation. But the whole process is quite simple if we do not talk about mathematics. We have a cute dog image, very accurate, right? And then we are trying to add some noise there. We add more noise, more noise, more noise. And after several steps, you can see this one, you cannot detect it's a dog, right? It's quite noisy. And for this noisy image, we know the distribution is the Gaussian distribution. Okay, and then we are trying to go backward to learn the distribution of noise. Yeah, so we're trying to remove some noise. We try to find the direction to how to remove the noise. So we are learning this score function until we can go back to the cute dog image. Okay, by learning this score function, then we can learn the distribution of the original image. So this is, yeah, ask ChatGPT for more details. The ChatGPT can also give you a lot of like mathematical equations. Okay, but just here I want to say this is a magic box diffusion model, and it works very well. Okay. However, if you want to apply diffusion model, it's very time consuming because it's like a lot of steps and they are trying to give you like members, a lot of members. It's like a guessing, right? Guessing what kind of combination you can get the accurate result. Yeah. So when we are doing this, we are thinking, no, it's too slow. And when we are looking at precipitation, this image, we found out there are some interesting areas, right? Heavy precipitation, but there are also some like boring areas without heavy rain. Yeah, for these boring areas, we actually don't have to use our diffusion model to apply it everywhere, right? So for this one, we use the wavelet transform. We try to break them down to like low frequency organization, high frequency organization, and then we apply our diffusion model specifically on this kind of high frequency areas to make sure for some heavy precipitation regions, we give more attention and it can like take more computational resources. Okay, then overall we can speed up this kind of computation. Okay, yeah, and so this is some data. I use MRMS, multi-radar, multi-sensor data sets, and this one is radar based. Okay, and so we choose the region in Oklahoma, and we only use like 5 months data from January 2021 to May 2021. Yeah, to train this model, and then we test this model in Oklahoma first. And here is the result. Oh, this is not my most updated version, but it's okay. For this one, there are several figures because in our paper, we need to show the comparison along with other models. But for this one, we can only focus on this one. This is ground truth, high resolution data. Okay, and the last one, WDM, wavelet diffusion model, is our product. Okay, as you can see, when we apply the diffusion model, for the high resolution is very similar to the original ground truth. Okay, of course, we also tried like UNet and EDM and other like Fourier EDM. Yeah, because mathematician said if we use a wavelet diffusion model, they also have to show the comparison between Fourier transform and the wavelet. Yeah, but for us, we only care about the high resolution, the ground truth, and what we got here. Yeah, so from my eyes, I think this figure is good, is reliable to use. Yeah, so this is like intuitively, results. We also put the statistics here. Yeah, we use different statistics index to show our wavelet diffusion model give the best statistics results. Yeah, very accurate. So this is case 1. And we also have case 2. Yeah, you can see it's like very accurately give you the high resolution data. Yeah, and also statistically it's the best. And also case 3 for another type of precipitation. And again, yeah, WDM, wavelet diffusion model is the best. Okay. So this is like 3 cases. We actually choose, I do not remember, maybe like 100 cases. Yeah, put them together and for each matrix, for each index, yeah, WDM is the best. Okay. And also I want to point out is for the flash flooding, right? The heavy rain is the most important, and this blue line is our diffusion model. Yeah, and this one achieved the best result in terms of the lowest absolute difference. Okay. Besides that, the WDM has the highest efficiency. Yeah, the newest version actually is like 1 meter. 1 minute, then you can get the results. But for the vanilla diffusion model, it takes like 10 minutes. Yeah, this thanks to the wavelet decomposition. Okay, so these are the strengths. And yeah, so we got accuracy, we also got efficiency. Now we need to focus on like generalization. Okay. So this one is very difficult. Yeah, we train the model in Oklahoma and then we applied it to different places. Yeah, because the time is limited, I just show like the overall results. Yeah, the Oklahoma, Illinois, California, Maryland, Florida, this is our method and this is target. And so here I just can assure you it works. So this model trained in Oklahoma and it can be transferred to other states. Okay, yeah, so I guess, okay, so it's like I want to invite you to collaboration. Yeah, so I'm putting some like more applications here. Yeah, for this diffusion model we published is like spatially. Yeah, we can also apply it to to temporally, right? To give like high resolution, not only in spatial, but also in terms of temporal. Yeah, we can get like a low resolution, but to put it to the it's like 1030, like 1040, 1050. Yeah, and then from this kind of coarse resolution, especially then to the high resolution. Okay, yeah. So, and what happened here? Okay, and also, my background is precipitation radar thing. So I'm very enthusiastic about precipitation microphysics. Yeah, so I'm thinking previously we use this kind of gamma drop size distribution, right, to describe the precipitation microphysics. And now we can try to use this diffusion model to replace the traditional gamma distribution. Yeah. Actually, this idea, when I typed my idea, yeah, my background, this kind of work to ChatGPT, before I asked ChatGPT already gave me this idea. Yeah. And ChatGPT said, Barry, maybe you can try this one. Okay. So that's it. I just leave it here.
Yeah, John.
Is this something that can be done and applied to like with live radar data? So if you had an area of the country that has poor radar coverage, like a radar hole, could this improve the quality of radar images, like images like during an event, or does it have to happen post event?
Depends. Yeah, because when you said about the radar hole, radar gap, I'm assuming this is because the adjacent radars are too far away from each other, right? Yeah. I can tell you is yes and no. You can use diffusion model to give you answers. The question is how reliable the answers is. And also, my PhD degree, my PhD dissertation is all about how to fill the radar holes. So I might personally actually believe physically based model can work better.
Yeah.
Yeah. But you can always, yeah. So now I'm thinking hybrid way, have some satellite-based spacebound radar to look down to get the profile of reflectivity to fill the radar gap. And also, but that is limited in terms of the vertical resolution and also the spatial quality of the radar. So if it can be hybrided with different model, I think it would be the best.
Okay.
Thanks.
Does the diffusion model use any covariates at all, or is purely using the image and the input?
Good question. So for the preliminary results, it uses the pure image. However, I'm trying to give more predictors there, yeah, to guide it because I did not from this one here. Yeah, I actually also tested the sea breeze event in Houston, but the results not good. Why? Because I use the precipitation cases in Oklahoma, and Oklahoma did not never see the sea breeze events. Yeah, yeah. So which means we need to give the model some guidance in terms of physics. Yeah, to tell them what could happen, what could be happening. Okay, yeah, but this is some future work.
Great, I think we're gonna end it here. Thank you
Okay,
so much,
thanks.
Barry.